To the untrained eye, picking a heavy weight off the floor looks like brute force. In reality, it is a highly calculated physics problem. It requires the synchronized contraction of massive skeletal loads, fighting directly against gravity. In biomechanics, we define this action as a closed kinetic chain compound movement. Because the feet are fixed to a solid surface, the body must recruit multiple major joint systems simultaneously to generate upward propulsion. As we see in this diagram, force originates at the floor. That ground reaction force must travel perfectly up the kinetic chain, from the ankle through the knee and hip and up the spine, without any energy leaking out along the way. By deconstructing these mechanics, specifically the neuromuscular recruitment patterns, the kinematics of your stance, and how different equipment alters the physics of the pull, we can engineer targeted strength development and preserve joint longevity. Resistance protocols involving heavy loads carry inherent risk. Review the clinical literature and consult a medical professional or certified trainer before applying these mechanics to your own body. To understand the strict science behind human performance, subscribe to the channel. The deadlift acts as a biomechanical bridge, connecting raw lower body propulsion with absolute upper body isometric stabilization. During the concentric phase, lower body movers drive hip extension. The gluteus or the quadriceps initiate knee extension. Simultaneously, the erectorspinae and core stabilizers lock the spine into rigid alignment. At the same time, the latissimusdorsi contract to keep the bar pinned tightly against the legs, preventing the load from drifting forward. Further up the chain, the trapezius muscles resist scapular dequession, keeping the shoulders securely in socket, while the forearm flexors clamp down to secure the grip. This intricate coordination relies on a mechanical curiosity known as Lombard's paradox. Under standard single-joint mechanical assumptions, if two opposing muscle groups contract at the exact same time, their forces cancel out, and the joint freezes in place. Look at the vector lines in this isolated model. In a closed kinetic chain movement like the deadlift, the quadriceps and the hamstrings do exactly that. They pull in opposing directions simultaneously. Rather than paralyzing the joint, this specific co-contraction results in highly efficient hip and knee extension. The tension across both joints dictates the upward rotation. The deadlift relies on this paradox. It requires maximum isometric stiffness in the upper body to facilitate maximum dynamic output in the lower body. The external torque placed on your frame changes the moment you swap the lifting implement. This diagram illustrates traditional barbell mechanics. A vertical line drops from the load center, and a horizontal line measures the moment arm to the lumbar spine. Because the steel bar stays in front of the legs, it generates high lumbar shear force. We can alter that geometry using a trap bar. By standing inside the implement, the load relocates to surround your center of mass. The vertical line moves backward to the midfoot, drastically shortening the horizontal moment arm to the lumbar spine. This reduced bar-to-body lever arm decreases the bending moment on the spine. It allows the lifter to maintain a more upright, quad-dominant posture throughout the pull. Substituting the bar for dumbbells introduces another set of variables entirely. Independent handheld weights remove the fixed symmetrical path of a barbell, introducing multiplanar kinematic freedom. Because each hand moves independently, the lifter must recruit minor upper back and shoulder stabilizers to control the load in space. This prevents the dominant side from compensating, forcing the weaker side to perform equal work, which actively corrects bilateral strength imbalances. Manipulating the implement is the most direct way to artificially adjust your center of mass. You choose the tool to prioritize either absolute neurological overload or spinal joint preservation. Once the implement is selected, shifting your stance and joint flexion angles. By understanding these mechanics, you can use knee flexion and hinge depth as precise mechanical levers, toggling the neuromuscular load between the quadriceps, the hamstrings, and the lower back.
A sumo deadlift utilizes a much wider foot placement, with the hands gripping the bar inside the knees. Research by Escamilla et al. Demonstrates why this matters. As the protractors in this comparison show, the sumo setup creates a steeper, more upright torso angle, resulting in higher activation of the vastuslateralis and medialis in the quadriceps. Because the torso remains more vertical from start to finish, the sumo style significantly relieves shear strain on the lower back compared to a conventional pull. For targeted hypertrophy of the posterior chain, we use the Romanian deadlift, or RDL. the lifter maintains a slight fixed knee bend throughout the movement, stopping the barbell at mid-shin. This applies an extreme stretching vector across the glutes and hamstrings. Crucially, the weight never touches the floor between reps. Avoiding ground contact maximizes eccentric loading and keeps the posterior chain under continuous time under tension. While similar in appearance, the RDL differs entirely from the stiff leg deadlift. The stiff leg variant utilizes nearly straight knees and requires the lifter to extend the range of motion all the way to the floor. This places intense, specialized demand on hamstring flexibility and forces the erectorspinae to work much harder to recover the weight. Bilateral lifting distributes load across a stable 4-point base. By removing one support point in a single leg deadlift, the body must manage rotational forces and maintain a level pelvis simultaneously. This unique stability requirement creates a proprioceptive stimulus absent in standard two-legged pulls. On this center of pressure grid, we can see balance fluctuating beneath the planted foot. To prevent the pelvis from tilting under the offset load, the gluteus medius must fire continuously. In this unilateral stance, the gluteus medius acts as the primary frontal plane stabilizer. If it fails to activate, the knee caves inward, a condition known as genu valgum. No matter the variation, lifting heavy loads exposes the body to specific biomechanical failure points. Two common form mistakes reliably cause injury. The first is allowing the barbell to drift away from the shins. A drifting bar artificially elongates the lumbar moment arm, multiplying the torque applied to the spine. The second failure point is a rounded lumbar spine under load. Look at this cross-section of the L4 and L5 discs. As the spine rounds into flexion, compression arrows pinch the anterior side, pushing the nucleus outward toward the nerve root. To defend against this failure, lifters utilize a specific biomechanical bracing technique, the Valsalva maneuver. By inhaling deeply and bracing the abdominal wall against a closed lattice, the lifter massively increases intra-abdominal pressure, or IAP. This internal pressure creates a rigid hydraulic cylinder out of the human torso, safely distributing extreme compressive forces away from the vulnerable discs. The deadlift serves as a clinical mechanism for aging humans to preserve independence. The mechanics used to manage a barbell are identical to the posture required to safely lift a heavy box from the floor. When the hamstrings contract, they pull the tibia posteriorly relative to the femur. This tension counteracts the anterior shear forces that typically stress the ACL, effectively stabilizing the knee joint under load. Furthermore, subjecting the skeletal system to heavy loads triggers biological adaptation. The bones rebuild themselves denser and stronger to survive the stress. This chart plots bone mineral density over a lifespan. As demonstrated in a 2021 study by Nguyen, the steep declining curve represents a sedentary baseline. The high, sustained curve shows individuals engaging in heavy, closed kinetic chain pulls, maximizing bone density at the hip and lumbar spine. By understanding moment arms, selecting the appropriate implement, and managing intra-abdominal pressure, you can safely load the skeletal system at any age. The deadlift is a strict science of angles and tension. When respected as such, it is a powerful tool for maintaining structural integrity, postural control, and physical autonomy for a lifetime.